Let us discuss some key terms related to cryptography. Cryptography is all about securing a message so that unauthorized persons do not have access to this message. It is also about keeping the message confidential. Confidentiality means keeping it secret. Cryptography is also about authenticating the person before sending the message. Only the authorized person should be able to view the message. Authentication, in other words, means we authenticate the user by using the password, username, or any other biometric. Non-repudiation means if a user sends a message, he cannot later deny it. So, non-repudiation in cryptography is achieved using digital signature. Integrity in cryptography means the message, once it is sent, the message should not be altered such that the contents of the message is changed. That means the message should be tamper proof. Next, encryption is changing the information from plain text into ciphertext. Plain text means it is the message which is to be sent to the sender, and ciphertext means the plain text we get after which is encrypted using encryption algorithm. Decryption means getting back the original message from the ciphertext. Cipher means it is the security algorithm used to encrypt the plain text. Cryptanalysis is the science of decrypting the plain text. Now, in cryptography, random numbers are very important. We'll see some properties of random numbers. Random numbers are widely used for secret key generation. Random number should have some requirements. The randomness of the random numbers should be widely distributed. That means it should be very random and not predictable. As you can see, each random number should be generated independent of its previous random number, and random number should be uniformly distributed over a certain range. As I already told you, the random number generated should be unpredictable. So if it is predictable, then the attacker can easily try to decrypt our message. Now let us see what is algebraic structure. Algebraic structure is a collection of non-empty set A, collection of elements, let us say the set is A, a collection of operations on that set, and finite set of identities. They are also called as axiom. So we'll see what are these. So there are three different types of algebraic structures. First one is groups, second one is ring, third one is field. So we'll see what each of these are, and we'll also see some example. As we already discussed, so group should be a non-empty set of element. Let us say we'll take the set as ABC. In group, only two operations needs to be satisfied, addition and subtraction. And in addition to these two properties, few axioms also need to be satisfied. We'll see what are those axioms in the next page. So if all those axioms are satisfied, then we call it as group. First axiom is closure. That means if you add any two numbers, the resultant number should also belong to that group. Inverse means any number, if you add it to the inverse of that number, you should get 0. So we'll see all these things in the example. Associativity means if you change the order of the operation, the result should not be changed. See here, as you can see, first we are adding A plus B. So then we are adding B plus C here. So this should not change the result. Then there should also be an identity element, like if you add that element to 0, you should get back the same element. As you can see, A plus 0 is equal to A, 0 plus A is equal to A. Now we'll see some example. See, set of all integers starting from minus infinity to plus infinity it is called as set of all integers, and it is represented by Z. Let us see whether this satisfies all the properties. For example, let us add any two numbers. Let us say we'll add 2 and 3. So if you add 2 and 3, the result is 5. As you can see, after 3, 4, after 4, 5. Isn't it? So 5 also belongs to this Z. So the first property is satisfied. Now let us come to inverse. See, 2 belongs to this Z, correct? Minus 2 also belongs to this Z. So if you add two numbers, then we'll get 0. So this is the inverse axiom. So that is also satisfied. Now we'll see associativity. See, for example, if you add 2 plus 3 and then add 5, or if you add 3 plus 5 and then add 2, so the result does not change here. So associativity is also satisfied. Then we'll come to the last one, identity. So 0 is the identity element. So if you add 0 to any number, you will get the same number. So as you can see, 0 plus 3 is 3. 3 plus 0 is also 3. So we can say the set of all integers Z, set of all numbers Z with the property plus is called as a group. Now let us see whether set of all natural numbers, that is only numbers from 1, 2, 3, 4, 5, is it a group or not? It's not a group. So can you think why? See here, it does not support inverse axiom. Inverse axiom in the sense, see for example, if I want to get minus 5, see 5 minus 5 is equal to 0, but minus 5 is not present in this group. As you can see, minus 5 is not part of n, because natural numbers means set of all numbers 1, 2, 3, 4, 5 and so on. Next we'll see what is a ring. So ring is also similar to a group, but additional properties should be satisfied as multiplication. That is the only change, and remaining things are all same. As you can see, there is a closure property, inverse property, associativity and identity axiom. All are same. Now let us take this example. Set of all integers Z. There are also additional properties, associative properties and distributive property. This is also same thing. First, if you multiply AB and multiply by C, or multiply BC and then multiply by A, the result does not change. So here also, if you change the order, the result should not change. For example, see here, 4 into 3, 12, 12 into 5, 60. So here also 5 into 4, 20 and 20 multiplied by 3 is 60. So the result does not change. So similarly, you can verify for distributive property also. Now let us see some ring examples. See here, Z is a ring. As you can see in the previous example itself, we have shown. Then let us see what is a field. In the same way, so field is similar to ring and group, but only additional operators which should be supported are division. As you can see, plus, minus and multiplication, they are already supported. So additional division should also be supported. See here, the properties are, so addition should be supported, additive inverse. See, additive inverse means if you add any two numbers and subtract the number, for example, let us say 5 minus 5. So you should get 0. That is the meaning of additive inverse. Multiplication should be supported, that we know. And what is multiplicative inverse? See here, if there is any number 5, if you take the reciprocal of that number, that is 1 divided by 5, so the resultant answer should be 1. See, please note down the difference. Additive inverse means, so 5 minus 5 equal to, you should get 0. Multiplicative inverse means you should take the inverse of that number. So 5 divided by 5, you should get 1. So here you should get 0, here you should get 1. As you can see, so set of all rational numbers. Rational numbers means numbers which are written in fraction, 1 by 2, 1 by 3, 3 by 4. So these are all called as rational numbers. As you can see, rational numbers, they are commutative with respect to addition. See, it doesn't matter if you add 2 plus 4, 2 by 4 plus 3 by 6 or 3 by 6 plus 2 by 4. The result does not change. In the same way, in multiplication also the result does not change. And For example, if you take 2 by 3, so 2 by 3 inverse is 3 by 2. So if you multiply them, you will get 1. So all the axioms are satisfied. So we can say the set of all rational numbers forms a field. So this is what they are written. Set of all rational numbers Q with operation plus, minus, division and multiplication is a field. Now let us see one still more trickier example. Let us see set of all integers mod 2. See, set of all integers means it is represented using z, mod 2. So now we want to find out whether z mod 2 is a field or not. See here, see we can z mod 2 means, see, whatever number you perform modulo to arithmetic, the answer will always be either a 0 or 1. So you can see 0 mod 2 is 0, 1 mod 2 is 1, 2 mod 2 is 0. So in the same way, if you go on like this till infinity, the answer will be either a 0 or 1. So we can write it as, so instead of saying z mod 2, we can write is 0 mod is 0 comma 1 a field. So instead of writing z mod 2, it is same as writing 0 comma 1. So we'll see whether 0 comma 1 is a field. First we'll go to the addition. See here, 3 mod 2 plus 4 mod 2. See, 3 mod 2 is 1, 4 mod 2 is 0. So 0 plus 1 is 1. 5 mod 2 is 1, 10 mod 2 is 0. So 1 plus 0 is 1. So the answer which you are getting 1. So that belongs to this one. Isn't it? So this satisfies the addition property. Let's go to the multiplication. 3 mod 2 is 1, 4 mod 2 is 0. So you will get 0. In this case also you are getting 1. So 0 and 1 both are belongs to this. Multiplicative inverse, as you can see 1 is the multiplicative inverse of itself. See, 1 divided by 1 is always 1. So we can say z mod 2 is a field. Now can you try one small homework? Can you try whether z mod 5 is a field or not? You let me know in the comment section.